Okay, we are here again, and no, wait, not this one, is this one, I have to show, okay. Now we present another example that compare the performance of two different fluids, water and air. So I imagine again a stream of a fluid over a flat plate. So in this today always flat plate, but I want to compare two cases. If the fluid is water and if the fluid is air. So the factor of the thermophysical properties. And with both fluids, I consider Ts equal to 20 Celsius degree and T infinite equal to 40 Celsius degree. We want to compare the performance of air and water. I evaluate at the beginning the film temperature. The film temperature, that is an average of the two values, 20 plus 40 divided by 2 equal to 30 Celsius degree. And I estimate the thermophysical properties for the two fluids. And I have density for air is equal to 1.149 kilogram each cubic meter. Dynamic viscosity for air is 18.72, but multiply 10 to minus 6 kilogram meter second. Prandtl number 0.7134. Thermal conductivity 26.32, but multiply 10 to minus 3 watt meter Kelvin. Observe the very low value of the thermal conductivity of air. Air is one of the best insulator. We will see in the course of next year of energy and building that air is used as a sort of insulator in windows, in ventilated facade, and so on. For the point of analyzing water, in the case of water, we have that the density is equal to, for that case, for that temperature, 995.61 kilogram cubic meter. Dynamic viscosity 797.7, that multiply 10 to minus 6. Prandtl number equal to 5.422. And thermal conductivity is equal to 615.4, but multiply 10 to minus 3 watt meter Kelvin. Okay, this is the starting point, evaluating at the temperature film the thermophysical properties of the two fluids. when you finish to copy, I change and I okay, now I want to start the comparison with the same U infinite. So in both cases, U infinite is equal to 5 meters second. And we want to identify the X critical. This is what I want to calculate, which is the X critical for the transition laminar turbulent flow. Okay, we know that the transition is for the Reynolds number, critical number, equal to 5, 10 to 5. We consider a sharp transition, a sudden transition from laminar to turbulence flow for this Reynolds number. So, Reynolds critical is equal to rho U infinite that multiply X critical, that is what I want to quantify or to calculate. So I solve for X critical and I obtain that is equal to Reynolds by me divided by rho U infinite. Now I have to calculate for air and water. So this one is calculated for air and for water. And X critical, substituting inside this expression the value of the thermophysical property of air and water. So what I change in the calculation, the dynamic viscosity and the density, give us that X critical is equal to 1.63 meters if I'm considering air, and X critical equal to 0.08 meter if I'm considering water. That means that for air, the first 1.6 meter is in laminar flow. For water, only 8 centimeters are in laminar flow. For water, nearly immediately, I start the transition to turbulent flow. And I'm interested also in estimating, so it's clear for all of you up to this point. And I want to estimate also the thickness of the boundary layer. And now I want to evaluate the thickness of a boundary layer for X critical. Sorry. How to calculate it? I know that the thickness of a velocity boundary layer is equal to 4.92 that multiply X divided by the square ratio or Reynolds number. Obviously, this one is for laminar flow, but I'm interested in the first portion of the plate for which I have laminar flow. Delta T is equal to delta that multiply Prandtl to minus 1/3. These are the two correlations that allow us in laminar flow to calculate the thickness of a boundary layer, velocity boundary layer, the first one, thermal boundary layer, the second correlation. Now I apply the two equations for my water and air case, and I have so I apply exactly this set of correlation for air and the same set for water. And I obtain, substituting nothing else, the X critical, the Reynolds number inside this one and the Prandtl number inside the second. I obtain that delta is equal to 0.011 meter, delta T is equal to 0.012 meter, and for water, delta is equal to 0.00056 meter, delta T is equal to 0.00032 meters. Obviously, the value of the thickness for water are smaller because also the length of the laminar zone is smaller in case of water, as a consequence also the thickness. If I consider that for water the length of the laminar flow is only 8 centimeters, I can imagine that also the values of the different thickness of the velocity and thermal boundary layer are much smaller than the case of air. I can change. Can I change? Now, I want to calculate, this type of exercises are very easy because I have only to apply correlations and definition, nothing to create or calculate in a different way than applying correlations. Now is requested the calculation of the shear stress, of the surface shear stress for X critical. And we know that tau S is equal to 1/2 of CF average value that multiply rho that multiply U infinite to 2. And CF L can be calculated using this correlation in laminar flow. But we consider Reynolds L equal to 5 that multiply 10 to 5. So for us, CFL is equal to 0.0000188. And as a consequence, considering this calculation, we can deduce that for air and for water, the surface shear stress is equal to 0.027 Pascal for air, and the surface shear stress is equal to 23.4 Pascal for water. Also, in this case, I have calculated the shear stress using only correlations. I have, starting from the definition of the surface shear stress, I have to estimate the CF coefficient. For this calculation, I use the correlation suggested for the laminar flow. I calculate it by imposing as Reynolds L equal to 5 by 10 to 5, that is the critical Reynolds value that determines the final point of the laminar zone, and I obtain for bath fluid this number, 0.00188. I substitute this number in the tau expression, and I have calculated, obviously, with the corresponding rho value for air and rho value for water, the surface shear stress for air and the surface shear stress for water. You immediately, if you compare the two values, you immediately notice that for water, the surface shear stress is much bigger than for air. Also, as a consequence, also the pressure drop will be bigger for water than for air. Now I have to analyze the heat transfer rate. So I'm interested in estimated before the H value, the Nusselt number and the H value, and then the heat transfer rate. Okay. In laminar flow, we know that the Nusselt number local value is equal to 0.332 Reynolds x 1/2 multiplying prime number 1/3, and hx is equal to Nusselt x that multiply k but divided by x. The average value of the Nusselt number is equal to 0.664 that multiply Reynolds L 1/2 that multiply Prandtl 1/3, and so the average value of the H coefficient is Nusselt L by K divided by L. These are the correlation to be used. Now I apply the correlation for the two fluids, in one case for air and in one case for water. Have you finished? And for air, Nusselt number is 210. Nusselt local value at the position corresponding to X critical. Average value is equal to 420. So if I want to calculate the average value of the H coefficient, I obtain 6.81 watt square meter Kelvin in case of air. So the transfer rate divided by delta T for each delta T, unitary delta T, is equal to HL that multiply to an area that will be considered L critical by 1, and I obtain 11.1 watt divided by Kelvin. So I'm considering again a length of my plate with unitary length in that direction, unitary wide of my plate. The fluid is this one, and I consider the area corresponding to X critical. So the active area in this case is referred to this length. The active area is this one, that is L corresponding to X critical, L critical, and 1 in the other direction. For unit delta T, considering a delta T between the fluid and the plate unitary, I can exchange 11.1 watt each Kelvin. For water, using the previously specified correlation, I have that the Nusselt local value at the end of a plate. So when I refer to local value X, I refer to the final point, the Nusselt number at the end of the laminar zone for the critical point, and I obtain 420. The Nusselt average means the average of the Nusselt number along the plate in the laminar zone. So this average value refers of the laminar zone from the beginning of the plate up to L critical. And in this case, I obtain 824, which with a corresponding average value of the convective coefficient H equal to 6,339 watt over square meter Kelvin. Why I have to consider an average value of the H coefficient? Because if you remember the slides, I have that this is the considered transition. This is the beginning of a plate. I have that ideally the shape of my H coefficient is this one when I have a sharp increase in the transition zone. This is H with X. So H decrease with X in the laminar flow. So I want to estimate an average value due to the fact that H changes continuously with X along the plate. And if you compare the value of the H coefficient for water and for air, is much bigger the case of water. Obviously, you can couple together the friction, so the pressure drop and the transfer rate. In the case where I have higher transfer rate, I have also higher pressure drop. If I want to estimate for this case Q, for unit delta T, again, HL that multiply L critical by 1, I obtain a value that is 507 watt each Kelvin. So much bigger than the previously calculated value for the air fluid. Okay? Momento. Is clear? At home is clear?
Yes, Professor, it's
Okay.
completely clear.
Okay, well, and now we go on in analyzing this example by considering a different length of a plate. So I want to consider a plate with 6 meters length. That means that I will have a portion of my plate from the beginning up to X critical. That is different, obviously, depending on the fluid, and then another portion up to reach the total length of 6 meters. So I will have a turbulent zone. Because 6 meters is, for both cases, bigger than X critical. That means for both fluid, I will have a zone with turbulent flow. In particular, I want to estimate the Reynolds number for L equals to 6 meters, and will be rho U infinite L 6 meters divided by me for air and for water. Reynolds number will be 1.84 by 10 to 6 for air. Reynolds number will be 3.74 by 10 to 7 for water. Turbulent flow in both cases, as expected, obviously. And we want to evaluate the thickness of a boundary layer. So, the thickness for the turbulent flow of a boundary layer is equal to 0.37, but multiply x, but multiply Reynolds x to minus 1.5. This is the general correlation. If I apply this correlation for water and for air, I obtain the thickness of a boundary layer at the length of a plate 6 meters equal to 0.124 meter for the air and delta 6 meter equal to 0.0679 meter for water. Much smaller for water than for air, the thickness of the boundary layer in turbulent flow. Now, now I'm interested in the convective coefficient and the friction coefficient, and I use now the correlation related to the turbulent flow, and in particular Nusselt average value for turbulent flow is equal to 0.037, but multiply Reynolds L to 4 divided by 5 minus 871 Prandtl 1/3. This is the correlation for the Nusselt number in turbulent flow, and for the coefficient CF, the corresponding correlation in turbulent flow is this one. So I apply the two correlations and substituting the corresponding numbers for L equal to 6 meters, I obtain for air and for water, Nusselt average value for the 6 meters equal to 2,620, and CF for air equal to 6 meter average value equal to 0.00319. For water, this corresponding value will be bigger because we find that for water I have a higher value of buffer, pressure drop, and transfer rate. .00222. Okay, the value of CF is smaller, but if I calculate the corresponding, now I calculate it, the corresponding tau S, surface shear stress, will be bigger. And I go on with this calculation. I have that H average value is equal to 11.5 watt square meter Kelvin for air, and H average value is equal to 7,625 watt square meter Kelvin for water. The corresponding tau S, the surface shear stress, is equal to 0.046 Pascal for air, and tau S average value is equal to 28 Pascal for water. Q divided by delta T is equal to 69 watt divided by Kelvin for air, and Q divided by delta T is equal to 45750 watt each Kelvin for water. So applying the corresponding delta T, I have that its transfer rate is equal to 1,308 watt for air, and is equal to 950,000, no, 900, wait, 15, no 50, I have 50 and then, okay, 15 watt, and the drag force that is equal to tau S by L by 1 is equal to 0.276 Newton for water, and the drag force is 168 Newton for water. So much bigger the transfer rate and much bigger the drag force of the two cases, of the water case with respect to the air case. It's okay? We do at least one example and then we, okay. one example, and then we consider if doing the final one or not. Okay?
All right, Professor.
Okay. So new example is again an airstream over a flat plate. No. And the air pressure is equal to 6 kilonewton each square meters. The temperature T infinite is equal to 300 Celsius, and U infinite is equal to 10 meters second. The length of the plate is equal to 0.5 meter. We have to estimate the overall heat transfer rate that we have to remove from the plate if we want to keep the plate at Ts equal to 27, I repeat now, wait. I want to keep the temperature of the plate equal to 27 Celsius degree. So, due to the fact that the temperature of a fluid that flows on it is 300 Celsius, I have to cool my plate if I want to keep the temperature equal to 27 Celsius degree. And I have to estimate this heat transfer rate. Okay? First of all, as usual, we estimate the temperature film and the property of the fluid at the at the film temperature. So, now we have to estimate the property at this temperature, but in the table that you can find in the handbook, in the book that you have of applied thermodynamics, for example, you find frequently the property at atmospheric pressure. So I have that for air at 437 Kelvin, 437 Kelvin, and questo l'avete già fatto con la Marchitto, questo esercizio identico? Probabile. And P equal to 1 atmosphere, che poi sono sempre gli stessi. Atmosphere, Ni, the cinematic viscosity is 30.84.10 to minus 6 square meter second. K is equal to 36.4 by 10 to minus 3 watt meter Kelvin, and the Prandtl number is equal to 0.687. We can consider that K, Prandtl number, and me, no dependence on P, but rho depends on P, and also Ni, that is Ni divided by rho, Ni that is Ni divided by rho depends on P. And how to estimate the law of dependence of Ni with P? we are considering air, so we can approximate air. Someone of you has the microphone on, because I switch off. Oh, okay, perhaps no, I cannot. I see some noise, but okay. I approximate the air like as an ideal gas. And I can say that P1 divided by ρ1 is equal to P2 divided by ρ2 at constant T. So for the ideal gases law at constant temperature, the ratio between the pressure and the density is constant. And now, if you finish to copy, I can change my okay. I have said that, wait, because the paint file does not answer to me. Okay, I have considered if Ni is constant, also the product density by Ni is a constant value. So ρ1 by Ni1 is equal to ρ2 by Ni2. And I have that Ni2 is equal to Ni1, ρ1, ρ2. Considering that ρ1, but also, wait. I can substitute the ratio between the density with the ratio between the pressures, and this is the law, the link between the kinematic viscosity and the pressure. So, the Ni of air at pressure equal to 6 kilonewton square meter is obtained by this is the new value of the kinematic viscosity at the pressure of my case, that is 6 kilonewton each square meter. That is different than the atmospheric pressure. With this value, I can calculate the Reynolds number. Up to this point is clear, is only applying the ideal gases law to estimate the viscosity at different situations than the value provided by the tables. I have to, with the new value of the kinematic viscosity, I can calculate the Reynolds number that include the value of the kinematic viscosity. And I have 10, that is the velocity, 0.5, that is the length that I have to consider, and the value of the kinematic viscosity. And I obtain 9,597. That is laminar flow. I select, knowing that is a laminar flow, the proper correlation for the Nusselt number, that is for the average value 0.664 Reynolds number, 1/2 by Prandtl number, 1/3 equal to 57.4. I deduce the HL average coefficient, and is equal to 4.18 watt square meter Kelvin. And finally, the transfer rate for unit wide, as usual, is obtained as 571 watt. So this example is very simple from the point of view of the application of the correlation, because you have only to estimate the regime and to select properly the correlation, that in this case is the correlation for the laminar flow. The unique strange point is the calculation of the kinematic viscosity for a particular condition. Okay? It's clear for all of you? Okay, now we have to do the last example. We start it because we are in time. And can I change? Okay, now this is a interesting, the more interesting example of this topic, that is a plate, a flat plate with wide 1 meter, that is maintained at the temperature Ts uniform equal to 230 Celsius degree, using electrical heaters, independent electrical heaters. Questo sicuro come loro l'avete fatto. Allora, so I sketch the system, and then I explain better the case. And I have Ts is equal to 230 Celsius degree. I have that the length of each heater is equal to 50 millimeters. Now I explain better the example. The fluid that flows on this plate is 25 Celsius degree as temperature, and U infinite is equal to 60 meter second. The case is represented in this way. I have a plate with a fluid T infinite and U infinite. The temperature want to be maintained at 230 Celsius degree. T infinite is 25 Celsius degrees. So I have to apply to my plate some heaters, some electrical heaters, because I want to heat my plate. And 1, 2, 3, 4, 5, 6. I have one heater, another heater, another heater, and so on. Wait, when I finish to draw, and so on. And first, second, 3, 4, 5, 6. Why I need to apply different ethers along the plate? Because the transfer rate coefficient H is not constant along the plate. The shape is like that. I will find that the transition is here. And so is decrease, then as a sudden increase at the middle of the ether 6, and then decrease again. This is H laminar, that is proportional to x minus 1/2, and H turbulent, that is proportional to x minus 1/5. Okay, this is the behavior, the trend of the H coefficient as a function of x is not constant, and so also the transfer rate by convection on the plate is not the same for all the points of my plate. And so I imagine to apply a different flux applied by means of the electrical ether to the different portion of the plate. So I select ethers that have this length. So each ether is 50 millimeters. The problem asks to us which is the ether that requests the maximum input. This is the request. The ether at which I have to provide the maximum electrical input. That means the ether that must provide the maximum heating degree to my plate to keep the temperature at this value, considering that the fluid flows at this lower temperature. The problem is clear for all of you now, because now we start with the solution. And
Yes.
okay, when we analyze, when we calculate, we have to identify first of all where is this transition. This X critical. We imagine, as usual, to simplify the analysis, to have a sudden transition for X critical. And we want to evaluate the position of X critical at the beginning. And we know that Reynolds critical is equal to 5 by 10 to 5. And this one is equal to U infinite, that multiply X critical divided by Ni. Okay, I solve for X critical, and for this case, I obtain that X critical is equal to 0.23 meters. This one is the X critical value for my case. Where is the X critical? Okay, if each ether has length 50 millimeters, means that for this critical value, the transition will be in the middle of the ether number 5, as I represented here. As a consequence, when I have to evaluate which is the ether with the maximum input, I can do some assumption. I can imagine that the ethers that can provide the bigger that need the bigger transfer rate can be or ether number 1, that is at this first part in laminar flow, which I value of H, or heater number 5, that is with 1/2 of lower value of H laminar, but with 1/2 with I value of turbulent H, or also heater number 6. So I have to compare the results for the 3 heater here in yellow, 1, 5, and 6, and then verify which is the heater that provide to us the higher heat transfer rate. Can I change the slide? Obviously, all the properties must be estimated at TF, that is 230 plus 25, divided by 2, the temperature film, 127.5 Celsius degree. Can I change? Yes. Now, I start with the heater number 1. So, heater number 1 is laminar. The length of the heater number 1 is 0.05 meter, that is the length of the heater, and I estimate the Nusselt average value with the laminar flow correlation. With x1 means the length of the heater 1. Ni and I obtain the value of 198 for Nusselt number. HL average value is Nusselt L by K divided by L is equal to 198 by 0.0338 divided by 0.05, sorry, that is our length in this case, and I obtain 134 watt square meter Kelvin, Kelvin. The corresponding heat transfer rate of a first heater is equal to HL by A. Okay, A is the L of the length by unit wide, TS minus T infinite, and is 1370 watt. This is the heat transfer rate for the heater number 1. Now I analyze the heater number 5. The heater number 5 is 1/2 in the laminar flow, 1/2 in the turbulent flow. So, which is the procedure? The procedure is evaluate the transfer rate from the beginning up to the heater number 5 with the correlation that now I write to you, that include both laminar and turbulent flow. Wait, and then I explain. for L equal to 5 by 0.05 meters. And that gives us the sense is, now I do again the sketch of my plate. 1, 2, 3, 4, 5, 6. Okay, heater number 1, 2, 3, 4, 5, and 6. I have that. Up to this zone, I have laminar. Then I have turbulent flow. I have that the heater 5 is in the middle of a transition. So to estimate the transfer rate of this heater, it is the heater number 5, I do this calculation. I imagine to consider the wall heat transfer rate up to this point, Q, and calculate this one minus what? Minus Q that I have to estimate up to this point. So the yellow, the orange one is up to, including the number 5 heater, minus the transfer rate up to including the 4 heater, to obtain only the transfer rate at the heater number 5. For the yellow, for the orange, sorry, heat transfer rate, that is this one. Adesso lo faccio orange meglio. Wait. Yes. For the orange heat transfer rate that include also the heater 5, from the beginning to the heater 5, I'm in a zone that include laminar and turbulent flow. So I have to calculate the Nusselt number using the correlation that include laminar and turbulent flow. And this one is the H coefficient. Can I change the slide? And ricordo più. So now I have to calculate the violet case, that was the heat transfer rate up to the heater 4. And in that case, I have laminar flow. So the Nusselt L up to the heater 4 use the laminar correlation. And the transfer rate of the heater 5 is equal to, okay, I can use the so if this can help you, and is what? 74, that was the transfer rate including the turbulent region, by 0.05, sorry. Wait, I add bracket to help you. This is the area up to the heater length 6. This is the area for the heater 5. Sorry. Is for the heater 5 and is for the heater 4. 5, 4, and this is the delta T, T S minus T infinite. And I obtain finally 1046 watt for the heater 5. That is less than for the heater 1. So the heater 5 for sure is not our selected heater. So it's not the heater with the maximum input. It's clear? Now heater 6. The last one that I have to analyze, the heater 6, and for the heater 6, I follow the same approach, but I have to estimate the Nusselt number for the heater, for the wall length up to the heater 6, that is, again, laminar plus turbulent flow. No, but L include L means average from the beginning of a plate. This I estimate using this correlation the average transfer rate from the beginning of a plate up to that point, and the value gives us 753, and as a consequence, HL is equal to 85 watt square meter Kelvin. Q heater 6 is now calculated as 85, that is this value, that multiply 0.3 by 1, and this is the area associated to the length up to the heater 6, minus 74, that is the transfer rate evaluated up to the heater 5, that multiplies 0.25 by 1, this is the area up to the heater 5, that multiply the delta T. And I obtain 1435 watt. That is the maximum value that I have obtained. That means that the winner is heater number 6. Okay? Heater number 6 is the heater with maximum input of the transfer rate. So that means electrical power that I have to provide to eat the portion of plate. It's clear for all of you? It's okay?
Yes, Professor.
Yes, Professor.
Ok. In classe? Tutto chiaro? Bene. Ok, no lesson on Wednesday. And because it's a graduation week, no lesson next Monday because it's the 1st November. See you the Wednesday of the next week. Okay, the 3 of November. Have a nice week. Bye-bye.
Bye.
Thank you, Professor. Goodbye.
Bye-bye.
Bye, Professor.
Saluti, prof.